Hello everyone, my name is Ryan Yassine Pike, and for this project I'll be analyzing the function f of x is equal to x times e to the power of negative x. This function is a product of a linear term, x, and an exponential term, e to the power of negative x. Its behavior is interesting because as x gets larger, the x term tries to make the function grow while the e to the power of negative x term tries to make it shrink towards 0. We will explore its limits, continuity, derivatives to understand its shape and find key points, and finally its integration to calculate areas. So let's take a look at the domain and the continuity of f of x equal to x times e to the power of negative x. For the domain, the function of x is defined for all real numbers, and the function of e to the power of negative x is defined for all real numbers. All real numbers. I'll just write it as an acronym. All real numbers. Okay. So that being said, therefore the product of this function is defined for all real numbers. Therefore, the domain is from negative infinity to infinity. Because it's all real numbers, therefore there's not a number that is left out to where there will be a discontinuity. So that's why the domain is from negative infinity to infinity. Now for the continuity, since x and e to the power of negative x are both continuous functions for all real numbers, their product f of x equal to x times e to the power of negative x is also continuous everywhere, which means that the graph has no breaks, no jumps, or no holes. There is no discontinuity within this function. The end behavior limits at infinity. What happens as x goes to positive infinity? Let me rewrite that as a limit. Limit as x approaches infinity of x times e to the power of negative x. We can rewrite this as just a limit of x approaching infinity, x over e to the power of x to get rid of that negative x. So as you can see, this is an infinity over an infinity situation, because if I were to just plug it in, it would just give me infinity over infinity. So this is a situation where we would use the L'Hopital's rule, taking the derivative of the top and bottom. So let me write that down. L'Hopital's rule. Where we take the derivative of the top and bottom. If I were to do that, the limit would now look like just 1 over e to the power of x, which is just 0 because it would be 1 over infinity, which just gives you 0. This means that there is a horizontal asymptote at y equals 0. As x approaches infinity, the function gets closer and closer to the x-axis on the far right. Now let's analyze what happens when x approaches negative infinity. So I can write that. Can we write that limit of x approaching negative infinity equal to x? Sorry. Excuse me. X equals x times e to the power of negative x, which once again, actually I don't need to write that. So if x is a very large negative number, like negative 1,000, for example, x is negative, and e to the power of negative x becomes a large positive number, which is just going to be a very large positive number. So a large negative times a large positive just gives a large negative. So if I were to plug it in, it would just look like negative infinity, because you would plug in negative infinity for all the x's in a limit. So it'd be negative infinity for x times e to the power of negative infinity, which negative negative means positive. Negative infinity times positive infinity, which just overall gives you a negative infinity number. So yeah, knowing this, so as x goes to negative infinity, f of x goes down to negative infinity. So keep that in mind. Now starting the first derivative and critical points. Next we'll find the derivative of x, to where the function is increasing or decreasing, and locate any peaks or valleys. So getting the first derivative, we can use the product rule. The product rule states that how you use the product rule, you will want to like make it into sections, whatever limit whatever you're trying to evaluate, you want to kind of divide into sections. Like you want to give variables. So when using variables, common variables they use is like u and v. So using these variables, you could use you can write it like this. Product rule states that you can you have to write it as the derivative of u times v plus u times the derivative of v. So this is known as the product rule. Very important. You would use it all the time. Okay. Now let's classify this, right? Let's say that u is x. Okay. Now let me just right here, just so you can still see it. Negative x. Okay. Let's classify u as x, and let's classify v as e to the power of negative x. Okay. Now we need to get the derivative, right? So that means the derivative of u would just be 1, because using the product rule, x to the power of 1, you bring down the exponent and you subtract it by 1. And for the letter e, the derivative of that would just be negative e times negative x, to the power of negative x, sorry. So now filling it in, change colors. Now you see that like little like prime or like apostrophe next to f, that means derivative f of x is equal to 1 times e to the power of negative x plus x times negative e to the power of negative x, which you could just simplify this. Let's just say e to the power of negative x minus x times e times e to the power of negative x. We can factor out e to the power of negative x and just get e to the power of negative x and in parentheses 1 minus x. Okay, so that's the derivative. Now we can evaluate the critical points where the derivative, write this down for critical points, where the derivative is equal to 0. Okay, where the derivative of 0, where the derivative is 0 or it's undefined. So we could just set it equal to 0. E to the power of negative x 1 minus x equals 0, and that's just saying so that the derivative of x equals 0. Okay. Since e to the power of negative x is since e to the power of negative x is never 0, it's always positive. So we must have 1 minus x equal to 0, because you would kind of try to separate the e to the power of negative x equal to 0 and 1 minus x equal to 0, but there's no point of setting e to the power of negative x equal to 0 because it's just always going to be a positive number. So it's quite pointless. So I could just write 1 minus x equals 0, which means that x has to equal to 1 when solving for x there. The function. So now we know that the function at x equals to 1 is f to 1 is equal to 1 times e to the power of negative 1, which is just equal to 1 over e. So the only critical point is just at 1, the y value will be 1 over e. Now we can analyze increasing and decreasing intervals in local extrema. Now, when we look at the sign of the derivative of the function, we got e to the power of negative x times 1 minus x. We know that e to the power of negative x is always positive, like I mentioned earlier. Okay, so if x is less than 1, for example, like x equals 0, that will just give us, that will just give us a positive number. And if you get a positive number, that will be greater than 0, right? So when it's greater than 0, that means the function is increasing at going on to negative infinity. Because since we mentioned that we're choosing a number less than 1, like 0, that means heading in the negative direction when evaluating, like with that number 0, it's always going to give us a positive number, which means it's greater than 0, meaning that at negative infinity, since we chose a number less than 1, since we're heading in that direction, right, because it has to be less than 1, so if you were to keep choosing a number less than 1, 0, negative 1, negative 2, negative 3, what's happening? We're going towards negative. That means, and you were to plug in that number into our derivative, you just always get a greater number than 0, meaning that heading towards negative infinity would be 1 when we use specifically 0. But now if we choose a number greater than 1, the negative number will be less than 0, right? So like for example 2. So you will just overall, when plugging into a function, you'll get a negative number, which is less than 0. That means when heading towards infinity, you will get, when you plug in at 1, the function will be decreasing towards infinity. So yeah, now for the local extrema, at x equals 1, write this down, local extrema at x equals to 1, the function changes from increasing to decreasing. That means the local maximum is at x equals to 1. The local maximum point is is 1, and just the evaluation at 1, which we wrote earlier, just 1 and 1 over e. Now second derivative in concavity. Now the second derivative will tell us about the concavity, whether the graph is shaped like a cup up or cup down, and help us find inflection points. We'll differentiate our first derivative by using the product rule again. So let me just e to the power of negative x, 1 minus x, okay? Now we, once again, using the product rule earlier, we give everything variables. So u is equal to negative x. V is just, v is just e to the power of negative x. And then just get the derivative of that again. U prime, v prime, just negative 1, negative e to the power of negative x. So, overall, when you write it all out, you'll do the double dash next to f to show the second derivative. Just to speed things up, I'll just write it all out. X minus 2. This is what you should get. It's the second derivative. Now, now we have the for second inflection point. Gotta set it equal to 0, the second derivative to find the inflection point. So, it would just be e to the negative x. X minus 2 equal to 0. Since e to the power of negative x is never 0, we have x minus 2, which equals 0. So solve for x, right? It just tells you that x is equal to 2. Since the function value at x equals 2 is just equal to 2 times e to the power of negative 2, this is just equal to 2 over e2. So we look at the sign of the second derivative, and remember that e to the power of negative x is always positive. So for the concavity, if x is less than 2, like if you choose number 0 again, you will get a negative number, and that negative tells you that it's concave down on negative infinity to 2. If x is greater than 2, if you choose a number like 3, it'll give you a positive value, and that'll be concave up on 2 and infinity. Okay. Inflection point, since the concavity changes at x equals 2 from downwards to upwards, the point 2 and 2 over e to the power of 2 is an inflection point. That tells us it's an inflection point. All right. So lastly, we find the antiderivative of the indefinite integral. So we're gonna make this an integral, an indefinite integral, and we're going to solve. So let's write x to the power of, x times e to the power of negative x, right? Okay. We're gonna, for this integral, we're gonna require a technique called integration by parts. By doing this, it should make it a little easier. Now we need to also, like earlier when we were determining like doing the derivative of everything, we got to divide everything up into parts. So let's use u again. Let's use u. And say u is x, right? So one of the variables, because we can split this into 2, right? I separated them by parentheses. Let's say u is x, right? And the way we can write this, it's just, is du of dx? Or, let's first write this. Du is just equal to dx, right? So if that's the case, we can say the du of dx is equal to x, which this is essentially the same thing. Now if I were to like try to manipulate the equation to where I could solve for dx, right? Should get du equals to sorry, you know what? Let's backtrack a little bit. And let's use the derivative. Let's also get the derivative of v, because we'll also say, let me write this first. V is e to the power of negative x. So we got u is equal to x, v is equal to e to the power of negative x. So then the derivative of v of dx, because this is the same thing as e to the power of negative x. And then let's rewrite the equation, solve for dx. So dv is equal to e to the power of negative x times d of x. And you just write as this, v is equal to the integration of e to the power of negative x times dx, which is just equal to negative e over negative x. Okay, so now that we got that settled, now we can just plug it into the integration of parts. So x times e to the power of negative x dx is equal to x times negative e to negative x, because that's what we said earlier, minus this. This is the formula for integration of parts. And if I were to simplify this, just to make it a little nicer, okay. Since we know that I wrote it earlier that the antiderivative of e to the power of negative x is just equal to negative e to the power of negative x. Now we can just write this. We can just rewrite it in a more simpler form. That negative x times e to the negative x is just negative e times to the power of negative x, and plus c. This plus c is very important. I can also simplify a little bit more. The c is for is the constant of integration when you're solving for an indefinite integral. So yeah, that's pretty much it. Covered the majority of tasks. We went over how to use the L'Hopital's rule, getting this first, second derivative, talking about the concavity, and later trying to solve for the antiderivative. That covers pretty much everything. I hope you enjoyed. Thank you for watching, and I hope this presentation clearly demonstrates the analysis of the function f of x equals to x times e to the power of negative x.